what happens when our data is in a contingency table, tables of counts. Right? So it's also very common, very popular in market research in particular. Canonical correlation is something we're going to learn in the second block. Don't worry about these terms not sinking in. I'm just giving you a very brief overview of what we're going to do. Right? Does anybody remember what I said before? This is canonical correlation here. Basically, it helps to summarize it. The hip wagging is just my idea, but it makes it more exciting. Canonical correlation is finding an axis. Let's say I've got a data matrix here. Finding an axis through that data. Right? There's a linear combination of those variables that maximally correlates with an axis through another set of data, another data cloud. Right? That's all it is. But with hip wagging. Discriminant function analysis, we'll get into that in great detail. Linear discriminant analysis. Partial least squares regression, I'll talk to you about that in less detail, but it's a very exciting technique used by chemists a great deal, in fact. So, what do we take away? These techniques all involve reducing high-dimensional data. And if you've got high-dimensional data, you've usually got complexity and structure in the data cloud. And that's what you're trying to find out. You're trying to find out about what's going on in this data cloud. What's the structure? Right? And we need some way of making it manageable. So one of the ways is to reduce the number of dimensions. It is difficult, in all honesty, it's difficult to present multivariate analyses to your line managers or somebody further up the scale who is completely naive to these techniques, right? So I will try and break it down like canonical correlation into something, into simple bite-sized techniques that you will probably pitch towards your boss at some stage if you need to them to understand very briefly what you're doing, right? But some of these techniques are very, very complex, right? And it takes a little while to get your head around. The important thing, it's important to know how to simplify your results, right? The best thing you can do is visualize your data, right? Multivariate analyses, because they are high-dimensional data sets, we have to work out how can we visualize this, right? How can we visualize this? You want to answer questions, what cases are unusual? What are the general patterns in my multivariate data set? Where is one particular entity relative to others? Should I be creating new products or targeting new audiences, etc., etc.? Lots of questions you can ask. And the best way to do this, if you can, is with a graphic. Right? So these are factor analyses and principal component analyses, colored by groups. These, hopefully, will be able to give you a narrative that you can tell to some audience, whether or not that's your boss, or if you're writing a scientific paper, whoever's reading it. Okay, so graphs are going to tell the stories. Pretty much every technique that we use, will have an associated graphic with it, right? That we can plot in 2 dimensions, in short. Okay, so you have to ask yourself, when you're dealing with multivariate data, what kind of variables am I dealing with? Qualitative variables, right? Group membership variables, or am I dealing with numbers? Most of the techniques that we'll learn are going to be to deal with quantitative variables. Right? Are there any a priori hypotheses? Right? Are you trying to test something? Just completed a analysis for a company with Masters of Analytics students, and they were doing what's called A/B testing. They wanted to know whether or not this kind of marketing was having an effect. Right? So they had a hypothesis in mind. Right? If I market to these people and not to these people, is there a difference in their consumer behavior? Right? That's when you have an a priori hypothesis. Or am I just interested in detecting a pattern of some kind? Right? That's not really an a priori hypothesis, you're just trying to describe what's going on. Sometimes it's not clear if you have a response variable or a predictive variable. Right? So just to restate it, I and other people refer to multivariate analyses as those methods dealing with multivariate response data, right? So your Y's are in multiple columns. Okay, so response variable is the subject of your hypothesis. If you do have a response variable, right? Your predictive variables are those variables that you might want to use to try and predict your response. They may be factors in an experimental design, right? Treatment levels. Hey, those people I've either marketed to people or I have not marketed to people. Right? I have given a drug to some people. I have not given a drug to other people. Case for example. It could be like an experimental design or just some other measured variable, covariable that you've got. So in general, whenever you do an analysis, there's going to be some underlying model behind it. And this model, the model that you choose is going to be driven by the questions that you ask, right? And remember, of course, whenever you model the data, your model is an approximation of reality, right? We can't, in all honesty, have a model recreate the full complexity of your multivariate data cloud. Let's take a step back. You guys know what when I'm talking about a multivariate data cloud, what I mean? Oh, I think there's some slides coming up. So, did I jump already? Oh, yeah. Okay. So I'll talk about the multivariate data cloud soon. It goes hand in hand with this idea about geometric interpretations of your data, I guess, and why we need to learn about matrices, which is what we're going to do for our talk today. So this is something that you should be familiar with, right? Here we have two variables, right, that I can plot in 2 dimensions, and I have a set of data points. So obviously for every data point here, it has a measurement on 2 variables, right? So it's a joint distribution. So this is, in 2 dimensions, sort of a flat data cloud, right? But let's say I had a third variable. That variable might project out of the screen, right? And then every data point would sit in this 3-dimensional space. Right? So that's more of a data cloud in a traditional sense, right? A cloud of data points sitting in this 3-dimensional space. Right? Does that make sense? So when I talk about data clouds, I'm just talking about, hey, look, I've got my axes defined by all my variables, right? And since every case that I have, every line of data has a value for every variable, it's going to sit somewhere in this dimensional space, right? And if it's 1 or 2 or 3 dimensions, I can plot that very easily. But after that, it becomes more complex. Right? So each variable is a dimension. Right? And every sample unit takes a value for every variable, right? So every particular row in my data matrix is a corresponding data point in my data cloud. Right? So you can represent every sample unit as a single point in space, in your high-dimensional space. Right? It's a very important concept that you guys have to grasp, but it's not a difficult concept. Okay? Every variable is going to have its own mean, right? Every numeric variable, I should say. You can't really work out a mean for a nominal variable. So, what I often talk about things like that's called a centroid, and that is simply the mean of this data cloud. So if I was to project all the data points here, so I'd look at all the y1 values, I will often interchange y1 and x1, right, if I don't have a specific hypothesis or response variable. So if I look at all of the y1 values and I calculate the mean of y1, and I do the same thing for y2, that gives me my centroid. Right? This is the middle, is one measure of the middle of the data cloud. Right? Directly analogous, it's a multivariate mean, is all it is. Right? So this is just the mean, right? That's just the mean. Together they make the centroid in my higher dimensional space. You guys with me? Yeah? Okay. What happens if we've got 3 variables? That's fine if we've got 2. Right, let's say we've got 3 variables. Let's look at this car data set where I'm looking at the number of miles per gallon it gets, the size of the engine and the weight of the engine, right? And I can, as I mentioned, my data cloud now sits in 3 dimensions, right? I've got the displacement, the weight, and the MPG. These are 3 different variables sitting in 3 dimensions. The data points are sitting in now in 3 dimensions, right? But of course, I'm not necessarily constrained to 3 dimensions. Typically, your data matrix is going to have a lot more than 3 variables. It may have hundreds. If you're dealing with some data sets, thousands. With computer vision, the stuff I work with, every pixel can be a variable. I could have millions of different variables in there, right? The centroid is simply the mean of each of those variables, right? And of course, you might be taking a sample of data. So you can get a sample centroid, right, just based on your sample data, and that is an estimate of the population centroid. So just as you will remember from stage 1 statistics, you have your population and your sample, right? The population is this hypothetical distribution, population mean is the hypothetical value of the mean if you were to measure everybody in your population, right? The sample is just what you've got in your particular data that you collected. So mu, I will use Greek letters to refer to the population values. This is standard notation. And we get our estimate of that, the sample centroid y bar. That's right. Just make sure when I canonical correlate. Right, so this is just our sample centroid, right? And it's just going to have a value for every variable, right? And this is just the mean of the sample centroid. Recall, it's just the mean of variable 1 and the mean of variable 2 altogether, right? So this is a, in 2 dimensions, it's just going to have 2 elements to it, and we can plot that in 2-dimensional space, 3 and 4. But of course, it can go up to as high a dimension as we want, right? And the mean, hopefully, you're all familiar with sigma notation, simply the sum of all the values divided by however many there are. I'll assume that you know what I mean by that. Okay, so a univariate analysis is when we have a response vector. Remember, a vector is going to be a single column, or perhaps a single row, depending on how you want to look at it, right? A univariate analysis is trying to find or characterize our response variable using our X data, our predictor data, right? And this can be multiple rows if we want it to be. But a univariate analysis takes the form where Y is a single column, typically, right? Just a single variable, in other words. So this is the notation that I'm going to use. If I have a vector, I will not use caps, right? So it's a single row, it's a vector. A matrix, I will use a capital letter in bold to denote that, right? So Y here is an n by p matrix. So what does that mean? It means the first thing, the n is the number of rows, right? And p is going to be the number of columns. So y11 is the element that is in the first row, first column, right? First row, second column, first row is the p, whatever, however many p is, right? So you all with me so far? Okay, so we'll typically talk about Y as being an n by p matrix, where n is the number of rows, n is usually the number of data points you have, and p is usually going to refer to the number of variables. All right, so typically we have n data points measured on p variables. Not always, but that's going to be the standard that I'm going to use. Okay? So in a univariate response analysis, right, we've got a vector denoted by X as a matrix, beta plus epsilon, right? So Y is a simple vector. X, if it's a simple linear regression, is going to typically have a column of ones that's going to refer to the intercept, and then we're going to have a row for every one of our a column for every one of our explanatory variables. So this would be a simple linear regression where we have one x, one column, one explanatory variable, right, plus an intercept trying to model our value of y here. Right, so beta naught and beta 1, you might remember when you're drawing a straight line, you need a slope and an intercept. What's the slope of what's the relationship relative of x and y, and then how do I center it? That's going to be the intercept. Okay, and of course, unless your model fits perfectly, you're going to have the bits that are left over that the model doesn't quite fit. Right, so this is if we want to work out, typically this is what we're trying to work out with linear regression. We want to work out what is the relationship between x and y, right? We want to solve to work out what is beta 1 and beta naught, in particular beta 1. How does y vary with respect to x? So to do things like solve for beta, we need to learn a little bit of matrix algebra, right? Even though this is not exactly the technique that we're going to be applying it to. Right, so just to nail it home, univariate, simple regression, we've got our response variable, and we're modeling with an intercept, a slope, a predictor variable, and then there's the bit that our model doesn't fit very well. Right. Multiple regression, as I've already talked about, is what happens when we try and model our response variable with respect to lots of x variables. Right, and so what we're doing, remember a regression is fitting straight lines, so if we've got a pair of straight lines, they define a plane. So essentially what we're trying to do is find the betas, which define a plane that best model the data. And with a regression, all we're trying to do is find that plane that minimizes, if these are the data points, the data cloud, we want to try and minimize the distance between the plane and the actual data cloud itself. Approximately, I mean, technically you're trying to minimize the squared distances, the sum of the squared distances, using OLS regression. Right, what happens if we have 3 explanatory variables, but one of them is a factor? Well, we can plot this still, right? Here we still have our response variable y, and then we have a couple of explanatory variables that are continuous, and then we've got another variable that might look like numeric, but actually it's just denoting some sort of group membership. It's a factor, and then it's the number of cylinders. That might be 4, 6, or 8, right? So it's just, I couldn't call it A, B, or C if I wanted to. The only way to really visualize this effectively would be, I guess one way would be to do a 3D plot. This is kind of an ugly 3D plot, and I could use color to denote the 3 different levels of the factor, number of cylinders. If you've got 3 variables and they're all 3 explanatory variables, right? So, and you're still trying to model a single y, you could potentially do the same thing with a color ramp if that last variable is also continuous. But things start to get ugly now and difficult to interpret. Right? So we've got some problems. So the main thing I want you to get out is this idea of a data cloud and some of the difficulties that you start to fall into, right? And we're just talking about 3 variables here. Right, so what do we take away from this, apart from the difficulties? Every variable is going to have its own mean. Right? Every variable is going to have some measure of its variance. Right? But that measure of its variance that we have is only with respect to the variable itself. Let me show you. We have 2 variables. Right? Each one is going to have a mean. So this is the mean of variable 1, right? This is the mean of variable 2. And then I've got some measure of the variation, right? I could look at this data just with respect to variable 2, right? And this is the spread of the data with respect to variable 2. This is the spread of the data with respect to variable 1, right? So each variable has its own mean and it's got its own variance, right? So you could easily calculate that. But it doesn't explain the fact that we have structure in this joint distribution. Right? What's the structure that's very clear from looking at this data? What do you think? Would you characterize the data perfectly, just describing its mean and each one's variances? Each variable's variance?
But the relation between the two groups?
Yeah, there is a relationship, right? And that relationship is that as one variable gets bigger, the other one tends to be bigger as well. They are correlated, in short. Right? So just describing the variance and the mean isn't enough. It doesn't capture exactly that. Right? So we need another measure. And that is going to be essentially how x varies with respect, x1 varies with respect to x2, or x and y. Right? So we could talk about covariances or correlations. Right? A correlation is simply your covariance standardized by the variances. So essentially the same sort of thing. There's going to be a slight distinction later on in one of the techniques. So typically I'm going to talk about means, variances, and the correlations between the variables. And this is going to create something that is going to be the underlying structure for pretty much all of our analyses. Right? It's going to be a model of the data. It's going to be called the covariance matrix, or the correlation matrix, if you want to use it. Right. So, what have we got? We've got, for any data cloud, now we're starting to talk about, for any pair of variables in that data cloud, we have the mean and the variance for that variable, but we also have the correlation or the covariance between that pair of variables as well. Okay, so now we've got every variable has its own mean and variance, but every variable has a covariance with every other variable. Right? So it's easy enough to do with just two variables. But now we're talking about this third thing. It's going to make things a little bit more complex. So for two-dimensional data, we're going to obtain, if we just describe the covariance, we're going to describe the variance of variable 1, the variance of variable 2, and how they covary together. Right? These three values are called, can be summarized in a matrix called the covariance matrix. And this is what the covariance matrix is going to look like. And we're going to get a bit of practice with this. Right? So let's say essentially that what a covariance matrix is a square matrix. Right? If you have, let's say we only have three variables, then P equals 3, and then we'd only have 3 columns and 3 rows. Right? So this is the variance of the first variable. This is the variance of the second variable. This is the variance of the third variable, right? If P was 3. This is the covariance between the first and the second variable. This is the covariance between the first and the third variable. And this is the covariance between the second and the third variable. Right? So you know that every combination of variables has a particular covariance. Right? And along the diagonal is the variation of each individual variable. Right? So now the diagonal describes the variation of each of the variables themselves, and the off-diagonal elements will describe the covariance between all possible pairs of those variables. Right? It's a very important structure. Don't worry, we're going to get lots of time with this. So it turns out, the covariance of any variable with itself is actually the variance. That's why we can write it like this if we want to. Right? So this is our model, and it is just an approximation of our data cloud. Right? It's going to be our model, which we are going to use commonly to describe the data cloud. And that's what we're trying to do. We're trying to describe data clouds, in essence, right? We're trying to characterize them. This is just one way of characterizing the data. So the covariance matrix is a model used to describe the data. There's a covariance matrix here, right? Here I've got 2 examples. This example here is, both are just using 2 variables, right? So I've got a data cloud here denoted by the blue spots. We have an amount of variation along this variable and an amount of variation amongst variable 2, right? And we can see there's a lot more variation on this axis than there is on this one, right? And I can see that in my covariance matrix. This is a 5, means that the variance is 5 for x, and the variance is only 1 for y here. Is there any covariance between these guys? Right? As x increases, does y increase? Not particularly, right? In fact, I know according to my model, that there is no relationship between the two. Right? So that's what my covariance matrix would look like for this sort of data cloud. Conversely, if I had a data cloud like this, right, now x1 is not very variable, x2 is quite variable, right? And so my variance in x2 is a 5, my variance in x1 is a 1, right? But still, there's no structure beyond that described by just each individual variable, right? There's no relationship between x and y here. As one goes up, the other one doesn't go up or goes down, right? So you see why so these guys, this is, sorry, the other thing I should say is these elements are mirror images of the elements above the diagonal are the same as the ones below, right? They're like a mirror image of it. And I'll show you an example. Here, clearly, we have some structure in the data, right? We can see here we actually have the same amount of variation along each variable. Here, it's a 3 and a 3, meaning that the variance of variable 1 is a 3, the variance of variable 2 is a 3, but there's also a covariance. It's a positive covariance, meaning that as one increases, the other one increases as well. So my covariance matrix is describing this sort of structure here, right? Positive relationship. Here is a negative relationship, right? So remember these two elements are always the same, right? The transposes of them, but we're talking about a negative relationship here. Okay? So the covariance matrix we'll get a lot of practice with. So what is a covariance? It's basically how each of the variables, like variable j and variable k, change with respect to each other. And I don't really expect you to memorize or know this math, right? But some of you might be familiar with the idea of a variance, which is just how data points vary with respect to their mean, right? The difference between an individual data point and its mean, squared and then summed across all of them, and then sort of averaged. That's what the variance is. Here we're doing the same sort of thing, but we're relating this difference for this variable with this difference for this particular variable. And the sum of all those and then average is your covariance, right? So what do those numbers mean? Well, really it's hard to tell because it depends on your variances, right? So it's hard to look at a covariance and interpret anything other than the fact that it's positive or negative. A positive covariance means that as one goes up, the other thing goes up. A negative is going to be as one goes up, the other one goes down. Right? But it's not on a scale that is easy to understand, right? Because it's on the scale of your variances, or your standard deviations. So, just as you can have a population covariance matrix, of course, typically we collect our data. Just a little time. We collect our data, and it's only a sample. And so that the model that we build is going to be just a sample covariance matrix. So this is the structure that we think is existing in the data set based on my sample. If I was to take a different sample, I would probably end up with a different sample. I would end up with a different sample covariance matrix, right? So this is going to vary from sample to sample. But they're all trying to estimate the true population structure of the data set if I had all the data available to me. Right? That would be the true population covariance. But we don't usually know what that is, right? Instead, we just have our sample covariance. Okay, so where are we? We've got the univariate data set. The univariate data set, right, if we're just trying to measure it with respect to different groups, then we've got a single response variable, and we're trying to classify it based on our groups. That's equivalent to analysis of variance. If we have a single response variable and we're trying to predict it with respect to a continuous y variable, we've got a regression, right? If we have multiple factors that we're using to try and predict y, we'll classify y, then we have multiple way ANOVA. And of course, if we've got lots of different explanatory variables and a single y, this is a multiple progression. Right, so I've gone through this. What we're going to be dealing with often later on is y is going to be a matrix, right? It's not a single response now, it's a multiple responses. So instead of a single column, we've got lots of y's. And typically, or often we'll also have lots of x's as well. Not always. Sometimes we just have the y's, and we just want to describe what's going on, and we don't have any particular x's. Right? And it turns out that actually a lot of the maths comes out to be pretty much the same. So if we have a matrix y, so this matrix, remember, is going to have p different variables in n different cases, right? We're trying to split that according to our groups. Right? That's equivalent to a multivariate analysis of variance. Right? It could be equivalent to a discriminant analysis if we wanted to. Right? Which is why a discriminant analysis could be considered to be a multivariate analysis. But often people think of the actual variable, that this thing, as your response. What happens if you've got lots of x's and lots of y's and these are all numeric? Right? Then we have something called a multivariate multiple regression. Right? So remember, a multiple regression has only got a single column of y's. Now we've got lots of columns of y's. The good news is that actually a multivariate multiple regression is the equivalent of doing a regression on each of the y's separately. You don't really gain much by doing it, in fact. What you can do is something called a canonical correlation, which was my little dance. That gives a slightly different thing. That's when you're looking at all the y's together jointly. Or we can do something called a partial least squares regression, might be even better. Okay, anyway, the point is, for a lot of univariate statistics techniques, statistical techniques, there is a multivariate analog, an equivalent to it. ANOVA and MANOVA, regression, multivariate regression, or I should say multivariable, I should say multivariable regression. Sorry. Okay, anyway, back to what we're talking about. The general properties of our multivariate data, right? So we know that each variable is going to have its own characteristics. And by characteristics, I'm going to talk about the mean and the variance of each variable. Then they have some degree of relationship with each other, right? And that could be, typically it's going to be modeled by the covariance or correlation, right? But if you think about that, that's a simple model, right? We're trying to, if you're just fitting a correlation to the data, what happens if the distribution, the joint distribution goes up and then down, right? So there's a relationship between x and y in my data cloud. I was to draw this like this. These are the data points in my two-dimensional space. What would my covariance matrix look like? Well, it would depend on the variance here and the variance here. It's going to give my diagonal, right? So that's going to be, you know, sigma squared 1 and sigma squared 2. But what's the correlation here? There's clearly a relationship between x1 and x2, but it's simply not well modeled by correlation. The correlation of that is going to be roughly 0. Right? So even though there's structure in this data, correlations are looking for linear structure. So we've already made this assumption of linearity in some ways. So we're throwing away some of the, by trying to simplify this, the data cloud, into a matrix, which is a model of the data. Remember, it is an approximation of what's going on, right? So this is a pretty strong assumption that, this assumption of linearity means we're going to misstructure like this potentially just by looking at the covariance matrix. But what are you going to do, right? No such thing as a free lunch. If we want to use these techniques, we have to make assumptions somewhere. This is one of the big assumptions. So we're just looking for, by using this covariance, we're just looking for general trends. As one variable increases, does the other one increase as well? Right? So when I talk about some relationship, I mean some sort of linear relationship. The direction and the magnitude of the response between the variables may be different for different variables. And obviously, as a consequence, the variables may not be independent of one another. But, so what we're saying is the columns of y, they may vary with one another, right? That's why we have the covariance. But the samples in themselves, they should be independent of one another, right? If they're not, then we have problems with our inferences. Right? So that's the idea of independence still is required, but it's for their sample units themselves, not for the variables. Right? We're trying to find, in fact, it will be advantageous for us to find variables that are in fact correlated. And I'll show you why tomorrow probably, or this afternoon. So, what are we looking for in multivariate data? Location. If you want to describe your multivariate data type to somebody, this is just the analog to what you do in univariate analyses. You look for